Thank you so much for having me today. My name is Daniel Tward. I'm an assistant professor here working in the departments of computational medicine and neurology. I spoke a little bit earlier introducing myself, and I said I like to study brain images and I like to focus on geometry. And so here's an application that I wanted to talk about today that we've been working on over the past year of how we can use geometry in deep learning to try to improve the performance and the reliability of convolutional neural networks. So this talk is called Moment Kernels, a simple scalable approach to equivariance in convolutional neural networks. And I'm going to walk through what some of the terms in this title mean, so it's okay if you don't know all the terms yet. All right, so what is the main idea? In general, when we have an image analysis task, the first thing we have is an image, which I usually, but not always, will use the letter I to denote the image. And we typically consider these images as functions from Rd to Rc, where d is the dimension of the space. And in medical images, that's usually 2 for a 2D image, like a radiograph, or 3 for a 3D image, like an MRI. And this is a function that maps to the space of pixel values. And the pixel values is going to be a list of C different numbers. So C could be 1 if it's just a grayscale image. It could be 3 if this is a red, green, blue image. Or it could be any other number if we're considering a sequence of feature maps that are often produced by convolutional neural networks. Now, what we're going to talk about here is apply some operation to the image. I'm going to call this operation F. And the output of that operation will be a new image. I'll call that new image J. So the equation here is J equals F of I. And the input is an image, and the output is also an image. So this is a pretty standard task in image analysis. There's a lot of different things we might want to do that fall into this framework. Maybe we want to blur the image. Maybe we want to brighten the image or improve its contrast. There's a lot of different possibilities. Now, when we're working with medical imaging data, we often have a problem of pose. So what orientation was the person in when they went into the MRI scanner and got a brain scan? And what's important is the properties of your brain, the disease we might try to diagnose, are generally independent I think this screen is fine and this screen is wrong. So this is throwing me off. Sorry about that. The properties of this image that we might want to understand are usually independent of the pose. So we don't care if you were lying down in the scanner or standing up in the scanner. We care if you have had a stroke or not. That doesn't depend on what your posture was at the time. So it's important to be able to generate machine learning techniques that are invariant to these types of changes. And I call these types of transformations of the input image a geometric transformation. And so here's 2 examples of geometric transformations. The original image is here on the left. And at the top right, a translation is an example of a geometric image. We're not changing anything about the pixel values. We're just shifting the whole image in one direction. This second example here is a rotation. This is another geometric transformation because we're not changing anything about pixel values. We're just reorienting the image. So maybe at the top, the person is standing up. In the middle, the person is lying down. But it's still the same brain, and the decision-making process should be the same. Now, I want to compare those 2 types of geometric transformations to a third type of transformation that we're not going to consider. So changes of contrast, for example, are not geometric changes. So over here, I blurred the image and I changed its brightness profile. And this isn't a geometric transformation, it's another type of transformation. So I just wanted to clarify that the bottom one here is also an important problem, but it's not what we're going to discuss today. So if we have a deep learning system or some operation F, and we change the input using a geometric transformation, what do we expect the output to change with? How do we expect f of I to be related to f of Ri, where R is some kind of a geometric transformation? So in general, there doesn't need to be any kind of relationship between them. Please go away. Sorry. In general, there doesn't need to be any relationship between them. But in many cases, there are very sensible relationships between them. As I mentioned, if the input is an image of your brain face up or sideways, and the output is your diagnosis, we would like your output to be exactly the same. So we'd like it to transform in a particular way, namely with the identity transformation. And there's other examples that we can go through there. So if the input is transformed with a transform R, like you see here, the output will be transformed with some function of R. What's important here is that this function of R is independent of the input image. It only depends on the transformation you apply to the image. So if this is the case, if when you transform the input, the output transforms in a particular way, we say that that function f is equivariant. So a couple examples, perhaps if we shift the input, we expect the output to be shifted by exactly the same amount. So that's very typical for image filtering, blurring, sharpening. If you shift the input, the output is also shifted. And in this case, the transformation that's applied to the output is the same as the transformation that was applied to the input. On the other hand, another example that I've alluded to a couple times, perhaps we shift the input and we expect the output to be unchanged exactly. And that's very common in classification tasks. And in this case, rho of R is just the identity transformation. So in this case, we say that f is invariant to that transformation, and invariance is a special case of equivariance. So to illustrate why I think that this is important and is particularly important in biomedicine, I wanted to build an example to show how machine learning and computer vision fails in certain types of simple tasks. So I wanted to use an example that we can all relate to, which is feeling like we're in pain and going to the hospital for one reason or another. And on the right-hand side is the pain scale, which is used at UCLA Health, as well as a lot of other hospitals. And in this middle row here, you can see how a person's face might look if they had different levels of pain, from 0 to 10. So typically, if you tell a person, rate your pain from 0 to 10, that rating isn't very reliable or reproducible. There's batch effects, like we saw a moment ago, depending on the person, depending on their background, their experiences. There's all different ways to interpret that. So this is an attempt to standardize it. So if you're a physician and you see a patient come into your office and you look at their face, you might want to say, which one of these faces is my patient expressing? And maybe we can train a machine learning system to classify that automatically. So this is really just a toy example here, but we're going to imagine that one of these 11 faces comes into your office, and we're going to train a machine learning system to assign them to one of these 11 categories. So the first very straightforward deep learning architecture we can apply here is just a multi-layer perceptron. A multi-layer perceptron is a sequence of linear transformations followed by pointwise nonlinearities. We apply them one after another. We make sure that the dimensions of the input and the output of each layer match up, and we get some kind of a classification. So on the left-hand side here is an example of a neural network coded in PyTorch to accomplish this classification task. We initialize 4 different linear transformations. We make sure that the number of dimensions of the input, which is the number of pixels, and the number of dimensions of the output, which is 11, are appropriate. We have some hidden layers, and in between each linear transformation, we apply this pointwise nonlinearity, which here is a rectified linear unit. A rectified linear unit means the pixel value is negative, you set it to 0. If it's positive, you don't change it. So this is a very common nonlinearity used in image analysis. So we can train a neural network using standard approaches, and we get an accuracy of classifying these faces. I added some random color and random noise to them. We get an accuracy of 100% and an area under the receiver operating characteristic of 1. So this is absolutely perfect. So a question arises, what if your patient comes in and they are a little bit shorter? So let's shift the input following this magenta colored line over here, just shift the input by a few pixels. And what do you think happens to the output of this model? Well, in fact, we don't do any better than chance. All we did is shift the input by a few pixels, and the model is completely destroyed. So does anyone have an idea of how we could solve this problem? Well, a procedure has been used in computer vision for a long time now, taking advantage of the fact that convolutions are translation equivariant. So here, instead of applying general linear transformations in between each nonlinearity, we can apply convolutions. So this is the difference between a multi-layer perceptron and a convolutional neural network. A convolution essentially says we take a filter and we apply exactly to the same filter to the image in every point in a sliding window fashion. And you can prove in a couple lines that this is translation equivariant just by writing out the definition of convolution. So we see if you shift the input by an amount t, the output will also shift by an amount t. So translation equivariance allowed us to build convolutional neural networks. Averaging across pixels is a translation invariant operation. So if we want to have an output of our network which is invariant to translations, one way to achieve this is just average across all the pixels. Then if you shift the input, the output stays exactly the same. So both of these techniques are used very, very commonly in deep learning. So we set up a similar network like before. Instead of 4 linear transformations, we now use 4 convolution layers. We separate each of them by this ReLU transformation. And at the very end, we take the mean over all pixels. So by design, we now have a neural network which is translation invariant, and every layer is translation equivariant. So when we apply this type of model to our data set, we now get an accuracy of 99.4 and an area under the receiver operating characteristic curve of 0.99997 before shifting the inputs. If we train this model on unshifted images and we test it on shifted images, we get exactly the same accuracy. So we have a mathematical guarantee because of this equivariance property. Now the accuracy is a tiny bit lower than the multi-layer perceptron, but this comes in exchange for a mathematically guaranteed invariance. Now, these types of convolutional neural networks, CNNs, completely revolutionized computer vision. A little bit of history. They've been around since about 1989, but they really became very popular in 2012 with the development of AlexNet, which demonstrated state-of-the-art performance in complex image analysis. So over the 10-ish years since then, they've become widely used in basically every image analysis application. Today, transformers is perhaps a little bit different, and there's some cases where CNNs are being replaced by transformers or in combination with transformers. So why was this done? Well, from my perspective, there's 2 reasons why CNNs are so much better for image analysis than MLPs. One is because they have a lot fewer parameters. If an image has n pixels and you're mapping from C1 channels to C2 channels, a linear layer has n squared C1, C2 parameters, and a convolution network only has k times C1, C2, where k is the number of samples in your convolution kernel. And that's independent of the size of the image. So these types of scaling laws are one reason why they became so widely used. But I think the key reason is really this translation equivariance, which is that when we look for features in the image, in order to make some kind of a diagnosis, it doesn't matter where those features are. We find them anywhere. We look for relationships in between them. But their position in the image doesn't really matter. So now I have a crazy idea. What if the person wasn't shorter, but they were lying down? They had their head sideways. So how can I recognize how much pain this person is in? If I apply my standard CNN, the accuracy I get is now only about 20%. So we went down from 99% all the way down to 20%. This is a little bit better than random guessing because there's some features like the high frequency content in these wiggly mouths, that a rotated version will respond in a similar way to an unrotated version. But in general, a CNN which is trained on images in one orientation will fail for images in another orientation. So why does the whole world use CNNs that are equivariant to translations, but nobody has cared? I don't want to say nobody, even though I just did. Significantly fewer people have cared to develop the theory of how we can make neural networks invariant to this other very obvious type of translation, or rotation. So there's a couple of reasons why this might be the case. CNNs were developed for analysis of these large natural image data sets, not really bioimages or medical images. And in many cases, natural images do depend on orientation. We don't expect them to be invariant or equivariant. Classic example is handwritten digit recognition. Everybody who does computer vision is familiar with the MNIST handwritten digit data set. Today, anyone should be able to code up a neural network in a few lines to get an accuracy very, very close to perfect on this data set. But what I learned when I started doing this project is that if you rotate a 6, you get a 9. I actually already knew that. But if you reflect a 7, and you are somebody who puts a second cross on your 7, you actually get a 4. That was a new one for me. For some reason, I never realized that. So if we designed a system for digit recognition and we built in rotation and reflection equivariance, we actually would do a lot worse. However, in medical images or microscopy images, the cells or the body can be imaged in any orientation, and orientation is generally not relevant, or is relevant only in a very simple way to the task at hand. This data set over here is an example of blood cells. I think someone may have shown the same data set before. And a classification task here is to take an image and assign it to one of 6 or 7 cell types. Obviously, when you put a blood cell on a microscope, it's floating freely in fluid. It can appear in any orientation. It can appear right side up or upside down. So you'd expect this classification task to be rotation and reflection equivariant in addition to translation equivariant. Okay, so I said that nobody is doing this, but that's not actually true. There's quite a few people who have tried to do it. It's just not common practice. So here are a few approaches to implementing equivariance to rotations and reflections in image analysis. The first is kind of the naive approach, which is data augmentation. Data augmentation is used a lot in image analysis. What we do is we apply transformations to our input data to kind of generate a randomized bigger data set. So if we have one image of a cell, we can train our neural network on all possible rotations and reflections of that cell, and then we would expect the classification to be independent of the orientation. Now this works well on average, but it comes with no mathematical guarantees. The difference between the best orientation and the worst orientation can sometimes be substantial. Another approach people have used is something called group convolution. What a group convolution is we expand convolution from dealing with pixels to also dealing with orientations. And our convolution kernels get bigger, and the number of feature maps get bigger, one for each orientation. So in 2 dimensions, we tend to have 8 standard orientations of our image. The axes can point in one of 4 directions, and we can reflect them, which gives us 8. Now, expanding your memory footprint by a factor of 8 isn't so bad, but in 3D, we actually have 48 of these. And typically in 3D image analysis applications, we're already memory limited. So this type of approach doesn't work well, number one. And number two, it only applies to discrete rotations. So rotations by 90 degrees, but not rotations by an arbitrary angle. Another approach people have used in the literature are using harmonic functions. So for example, if you deal with sines and cosines on a circle, where one is real and one is complex, if you rotate the input, the output is multiplied by a complex phase. And people have constructed methods for these to work in similar applications in 2D. And instead of sines and cosines, we can do something similar with spherical harmonics in 3D. And there's one other topic which follows a similar train of thought as to what I'm going to propose, based on matrix representation theory. And this is an idea of how you can sort of define Fourier transforms on matrix groups. Unfortunately, the mathematics behind this theory is quite complicated. Most people who would use this mathematics, who would use these types of neural networks, probably wouldn't understand the mathematics, which comes at the intersection of differential geometry and Lie groups and Lie algebra. So this is an example of an incredibly beautiful paper, a Wigner-Eckhart theorem for group equivariant convolution kernels. I think it's a beautiful paper, but the methods that they propose are quite challenging mathematically. And maybe this is one of the reasons why equivariance to rotations hasn't been adopted by the community to nearly as much of an extent as equivariance to translations has. So the goal of my work that I'm presenting today is to design a new approach to achieve equivariance to rotations and reflections. Now, this approach is going to use standard CNN machinery, so I'll show you the code for generating a network. It's going to look exactly the same as the previous code I show you. And it's going to rely on two important ideas. One, the features that we use when we're analyzing our images are going to be interpreted as geometric quantities. So these will be scalar fields, vector fields, matrix fields. And two, we'll put some relatively simple constraints on the types of convolution kernels that we're allowed to use. This approach is going to scale well to higher dimensions, and it's only going to use standard calculus and linear algebra. So here's an example of how we can code a rotational equivariant neural network using moment kernels. Just looks just like before. The one difference is we can't use the ReLU function anymore. The nonlinear linearities we apply will now depend on the magnitude of a vector or the magnitude of a matrix, as opposed to the individual components. And in this framework, our accuracy is 98.6%. Our area under the receiver operating characteristic curve is almost 1. So again, with a tiny penalty on accuracy, we've now gone from 99% to 98%. We can achieve a mathematically guaranteed invariance. Okay, so I want to talk about those two main ideas, how we represent our features and what constraints we're going to put on our kernels. So our features here are going to be modeled as what I call a geometric function. So an image where the pixel values are not gray levels anymore, but the pixel values are now the components of a vector or the components of a scalar. Now, what is the difference between a vector field, for example, a two-dimensional vector field, versus a list of two scalar components? And this figure that comes from the complicated paper that I just mentioned, which I think is beautiful and has very good figures, illustrates this idea. On the right-hand side, we see a cell here. They apply a transformation. They call that transformation G. I called it R for a rigid transformation. If you rotate the cell, these features, circles, they rotate with the cell. But if our features are vector field valued, when I rotate the image of the cell, the features change. The components of the features also rotate. So the image is rotating and the components of the feature maps rotate in an equivariant way. So this gives us equivariant transformation laws that are reasonably intuitive. You know that if you have an image of an arrow and you rotate the image, the direction of the arrow already rotates. That's intuitive. Now we need some kind of a linear map, which is a map from these geometric features to another set of geometric features. It's going to be something like a convolution, but we'll put constraints on our convolution kernels. So the constraints that we derived in our recent work lead to kernels of this form. K of x equals some function that depends only on the magnitude of x, and we will have to learn the parameters of that function. And the vector or matrix or tensor components are all just these products of the components of x. So we only have to learn one radially symmetric function with a few parameters, and then all the details of orientation are just copies of x one after another. That's one such moment kernel. There's another thing we can do to generate new moment kernels, which is take any pair of those x's and replace them with the identity matrix. So on the bottom row, it's an example of another moment kernel, where we have taken those first two copies of x and replaced them with the identity matrix. Okay, so I wanted to go through the math in two cases, which are relatively simple, and then I'll do just a basic sketch of the proof that we have in a related paper, which I linked to on the schedule. So when we're looking for an equivariant kernel that maps between scalars and other scalars, we can write out the definition of convolution. We can apply a rotation to the inputs and outputs. Then we make a change of variables in our integral, and we see that this rotation now appears in the kernel instead of appearing in our image. And we have an input f and an output g, just like our first equation. So if that's true for all f and g, it means these kernels are equal. Therefore, k of x equals k of rx. So this gives us a constraint we need to put on our kernel, and a radially symmetric function satisfies that constraint. Now, radially symmetric functions are not very detailed. We want more complex neural networks, which is why we build them up using vectors and matrices and higher-order tensors as well. So here's another example where we consider a mapping between vector fields and other vector fields. We can start out by writing out the definition of convolution. Here, u and v are vector fields. So this convolution kernel is a 2x2 matrix. Convolution kernel is not a scalar-valued function anymore. We apply a transformation on the left-hand side, and on the right-hand side, I'm reorienting the components of those vector fields. I'm not just transforming the image. We can rearrange things, and we see the same relationship as before. In this top equation, we have u as an input and v as an output. This next equation, we have u as an input and v as an output. Therefore, the kernel must be the same. We've derived this constraint, k of x equals r transpose k of r of x times r. And we can find two moment kernels that satisfy this constraint. One moment kernel, which is a radially symmetric function times a second power of x, and another one where we replace those two x's with identity. Okay. We call these moment kernels because we're integrating against them times powers of x. And when we do that, that's kind of the idea of the first moment of a distribution is we integrate that distribution times x. The second moment is we integrate it times x times x. That's where the name comes from. So in our paper, which is linked to here, we sketched a general proof to prove two things about moment kernels. One, convolution with moment kernels is an equivariant transformation for tensor fields of any rank. And number two, kind of the converse of this, is that if any kernel gives an equivariant transformation, it must be a moment kernel. Now, the idea of this proof is to consider transformations of an image which leaves certain points invariant, just like the two examples I showed you. We use those invariances to derive constraints. We loop through all the possible basis vectors of these kernels and show that the only ones that are non-zero are the ones that satisfy those that are moment kernels. So let me just show a few different examples of how we apply these. We build a neural network architecture where we use a block design where we take scalar-valued features, vector-valued features, matrix-valued features. We act on them with different moment kernels and get scalars, vectors, and matrices as an output. We stick these together, and for all the experiments I'm going to show here, we just used 8 layers. We stick them together blockwise here. Our input image is always a scalar-valued image. I colored it red. And the output image is going to depend on the task. It's going to have different characters depending on the task. So I'll just show you a few examples. The first thing we looked at was the Derma-MNIST classification dataset. This is a really nice dataset, the Med-MNIST dataset. It's just medical images kind of shared openly in the style of the handwritten digit, these very small 28 by 28 images. They also share the performance of some standard state-of-the-art deep learning models on performing classification tasks. So what's important is the classification task should transform like a scalar, which means if I rotate the image, the label should be exactly the same. So we applied our neural network over here. This bar here shows the area under the receiver operating characteristic curve for our network applied without data augmentation. To the left over here is our neural network applied with data augmentation. And you can see here that applying data augmentation, randomly rotating your training data set, helps you do a little bit better here. And we compared that to a standard architecture, which is the same thing shown in these two blue bars without equivariance built in. And the standard architecture without data augmentation does very poor, and with data augmentation does a little bit worse than our architecture. The other green bars show the area under the receiver operating characteristic curves for the other methods that were shown. On the right-hand side, we show the same thing but with accuracy instead of area under the receiver operating characteristic curve. And in purple, I'm showing something that I call worst case accuracy. So if you get unlucky and an image of your brain shows up in the worst orientation, how accurate will your classification be? And you can see that in our approach, the accuracy and the worst case accuracy are exactly the same. In the standard approach, even though accuracy can be pretty good, the worst case accuracy is pretty terrible. So on average, you do well, but if you happen to be an unlucky person going to the doctor that day, we might do quite poorly. Now, the next application that we looked at was image registration. Now, the idea of image registration is to take an image of your body and reorient it into some standard orientation. In brain imaging, we use an orientation called RAS, where the first axis points right, the second axis points anterior, and the third axis points superior. And a common task is to find an affine transformation, so a 3x3 linear transform and a 3x1 translation vector to put your brain in standard orientation. Now, the equivariance of this task is that every column of that matrix should transform like the components of a vector. So we took our model here. We have an input image in the left column, and you can see that the brain is oriented in a random orientation. Our goal is to reorient it into standard orientation on the right, RAS orientation. And in the first column here, we show the results of our network after training. In the second column, we show a standard network. And what you can see is that the error is much worse for the standard network than for our network. During the training procedure, we also train this network more than an order of magnitude faster because it already knows these equivariant properties that the other network has to discover. One more example I wanted to show quickly before I wrap things up is the idea of cell segmentation. So we use the YOLO model, the You Only Look Once object detection framework. This is a sequence of filters applied to your image such that the output gives you a bounding box. For each bounding box, it gives you a translation vector, so where should it be located, some scaling vectors, how big should it be, as well as some information about the cell type. Now, a rectangle cannot be rotation equivariant because if you rotate a rectangle, you get a diamond, which isn't a rectangle. So we modified this to output ellipses instead of rectangles. And we output a few different parameters: the type of cell, which is an invariant, the expected overlap of our bounding box with the cell, which is an invariant. We output two shift parameters: where should the ellipse be, which should transform like a vector. And we output a 2x2 matrix, which is a quadratic form defining that ellipse. And this quadratic form should transform like a matrix behaves under a change of basis. So there's a rotation matrix acting on the left and the transpose acting on the right. We trained this network and applied it to a simulated data set of cells. Our example is shown here in the second column. I know I'm running out of time, so I'll skip a couple things. On the right-hand side, what we see is the output of a standard network where we have flipped and rotated our image 8 times. And if you look in certain areas, you see, depending on the orientation, a standard neural network gives the same cell different labels. It gives you slightly different information about the position of the cell, and it's generally inconsistent depending on how we're looking at it. So, in summary, we developed a new approach for equivariance using geometric features and moment kernels as maps between them. We proved that all such equivariant convolution kernels must be moment kernels. We implemented architectures for 3 different tasks in bioimage analysis, and all of them naturally require a different kind of equivariance, which we can bake into our neural networks instead of having to learn from lots and lots of data, which in biomedicine we typically don't have access to. Now, I believe that this simple, in quotation marks, I don't know if you agree with me or not, this simple approach may help the adoption of equivariance into biomedical applications and improve trust in AI. So trust here says, if I go to the doctor and I'm lying down, I'm going to get the same diagnosis as if I went to the doctor and I was standing up straight. Feel free to go to my GitHub repository. The code walking through this pain faces example is there, so you can download it and run it yourself if you would like to. And I'll just quickly acknowledge some of the students who helped me with this work and some funding for related tasks. Thank you very much for your attention.